All right, good afternoon, everyone. You all know me now, so we can skip introductions. Just one word of warning. It's always day 2 of long international travel that's my weakest day, and indeed, I'm definitely feeling the 7-hour time difference today. So I don't think it's bad enough that I will fall over and start snoring, but I can't rule that out, so just be aware. So today, the first of my 2 lectures is going to have a bit of overlap with some of the things that Badri talked about this morning. And it also, I hopefully, will serve as an introduction to some of the topics that Nurgas Mavavalo will be discussing tomorrow. So I want to talk about aspects of wave detection kind of from the standpoint of the fundamental physics that we use to understand how a gravitational wave interacts with the detector. And I'm also going to describe a little bit of some of the underlying physics that we use to understand the operating principles of the detectors themselves. Nurgas will go into a lot more detail of that, but I want to give you enough of a sense of this so that you can appreciate some of the different elements that enter into that spectral density of noise that played a very important role in Badri's talk this morning. So, make sure this is on. So let's just begin. Okay, so we're going to talk a little bit about both ground-based detectors, and I'll say a few things about space-based detectors as well, since that is going to be particularly interesting and important over the next decade or 2. So I want to begin with essentially an answer, or doing a little calculation, which I assign all of my students when I teach my first-year general relativity class. And there's a right way to do this calculation and a wrong way to do this calculation. So what we would like to do is understand, if I have a gravitational wave detector that's sitting on the ground, and let's line up everything so that it's perfect. I have a source up here, and gravitational waves propagate down, go right perfectly aligned with the detector so that the polarization lines up perfectly. How will the gravitational wave respond to this? The naive answer, and I should emphasize that the answer and the outcome that I'm going to show you in a moment is something that one of the wonderful things about being at a university like MIT is that my email is in the public domain. And so various people have emailed me this little calculation. They've basically just learned enough general relativity to be dangerous. So here's the idea. I take my gravitational wave field. I've worked this out using the tools that I went through yesterday. I'm imagining that the waves, that the masses in here, I'm going to treat them as being freely floating test masses. And what I want to do, an object that is freely floating in general relativity, we treat as living on a geodesic of that space-time. And so I want to compute what the properties of the geodesics are as on these masses as the wave passes by. One comment that needs to be made. Now, if I am talking about a ground-based detector, they're obviously not actually freely falling. Okay? They're on pendulums. When I am talking about space-based detectors, the masses that go into, that will be going into the LISA spacecraft, and that are in fact in the LISA Pathfinder spacecraft, which was used to demonstrate some of the technologies and whose results I will show you later in this lecture, they are in fact actually freely floating. They are falling through space, essentially unaffected by anything but gravity. In a detector like LIGO or Virgo, they are not freely floating, but they are effectively freely floating in directions orthogonal to the normal to the Earth. Okay? So obviously, you're suspending them. If they were freely falling, well, they would freely fall for about a 100th of a second, and then they would crash into the floor. But if they are well-designed, if they are hanging on well-designed pendula, we can treat them as following a geodesic of space-time in the directions directions orthogonal to the normal to the Earth's surface, and as long as we only consider frequencies that are above the pendulum's natural frequency. So the pendula in LIGO have a natural response frequency that's several hertz, and so as long as we're looking at frequencies that are significantly higher than several hertz, if something comes along and wiggles them, it's essentially decoupled from that pendulum, and so it is accurate to treat them as freely floating in this regime. All right, so with that aside, we're now going to calculate the geodesic that these guys would follow. Okay, so as I said, we're going to imagine they're freely floating and compute the properties of these geodesics. This is a standard exercise that is learned essentially in the first couple weeks of studying a general relativity class. You work through the connection coefficients for your space-time, which I'm going to treat my space-time as just flat space-time plus this gravitational wave. I couple it to the velocities that these guys are following. And the answer is that the acceleration that the masses experience is given by the time derivative of the gravitational wave field times the velocity plus some corrections that go as the wave field squared, the velocity squared, the wave field times the velocity. Now, I start out with these guys initially at rest. So this tells me that the test masses in my gravitational wave detector experience no acceleration. The test masses remain fixed. Therefore, they are unaffected. Therefore, there is no effect. Therefore, LIGO cannot measure anything. Okay? This is exactly the emails that I've received, as I said, from people who have just learned enough general relativity to be dangerous. It's misleading. What this is actually telling you is that the coordinate systems that describe these things' motion are themselves essentially oscillating. Okay? What this tells me when I compute that geodesic is it tells me about the motion of these test masses with respect to the coordinates that define freely falling. And since they are essentially attached to those coordinates, yeah, there's no effect. It's kind of like saying, I'm going to define the origin of coordinates as me. I'm still at the origin of coordinates, so I'm not moving. I'm not moving. I'm at the origin of coordinates. That's essentially what that coordinate system has just done. What we need to do is put together a calculation that actually pulls out what something you can measure is going to be, not something that's tied to a specific coordinate system. A simple thing we can do is examine what the proper separation of the test masses will be in this coordinate system. So I have them at the ends of these arms here. And the way to compute the proper separation, so let's say I want to know the distance along the x arm here. You go into general relativity, you imagine an instant at a particular instant of time. So I'm going to look at no time-like interval, and I'm only measuring distances along the x-axis. And I integrate up a particular component of my metric to get the proper separation of the test masses along this. Okay, so this is just going to be given by this. H is a very small number, as we have emphasized, so it's okay to use the binomial expansion here. And so what I find is that the oscillation in the separation of the masses along the x arm is simply given by, up to a factor of order unity here, this polarization of the gravitational waves. If I repeat the exercise for measurements along the y-axis, I get the same result up to a minus sign. So the wave definitely has an impact on something. What we need to do is formulate how we're going to pull that out in terms of, we need the right tools. We want to formulate it in terms of what we can actually measure. So as Badri emphasized, and I think Nergis is going to emphasize in hers as well, the thing that we use to measure this is the phase shift that is imparted to the laser that propagates down these arms. So what I'm going to do to go through this in a little bit more detail is I'm now going to specialize to a detector whose arm lengths are shorter than a gravitational wavelength. That is the case for the LIGO detectors and for the Virgo detectors. They are making measurements where their shortest, the highest frequency that they're sensitive to is several hundred hertz. At several hundred hertz, the wavelengths up to, say, a kilohertz. Let's say a kilohertz. They're sensitive up to about a kilohertz. And at a kilohertz, the wavelength is 300 kilometers. These arms are 3 kilometers, 4 kilometers. Great. So I have a separation of these length scales. What we can do then is introduce what are called Riemann normal coordinates that cover the entire gravitational wave detector. I mentioned here that in this description I'm going to neglect the Earth's gravity and treat the detectors as free fall, and this is exactly the comment I had made before. In fact, you can actually include in the curvature tensor that enters into this, you can include the gravitational metric, the field of the Earth itself. And that's fine because it is effectively static. You can include things like the moon. Okay, that's not static, but it has a period of twice a day, or once a day. Well, its tide is twice a day. Okay, so they are all the terms that are not gravitational waves enter at very low frequencies that are out of your band. So again, as long as we focus on the frequency band that we're interested in, this ends up being a very useful tool for us. So a standard exercise that we do in this case is we compute the Riemann tensor associated with the gravitational wave field. And the only non-zero components are the ones that take this form. 0 stands for the time-like direction, spatial direction I, time-like direction, spatial direction J. And it's related to the gravitational wave field like so. I can use this using the equation of geodesic deviation. I can compute how the separation of these geodesics actually varies, what the proper separation and the variation of these geodesics is. And I get a relationship between the length of arm the length of arm J and the change in the length of arm I. And when we put it all together, we get a very simple relationship that essentially tells us in somewhat more sophisticated language that the shift in length of the arm of a gravitational wave detector is related to the unshifted length by the gravitational wave field. So this is all nice. And now I'm going to repeat a few of the things, so I'll go through this fairly quickly, but this is stuff that Badri reviewed in his lecture this morning. So the key bit, which is important here, is that we considered a relatively unrealistic, not even relatively, an extremely unrealistic configuration, a source that's exactly above our detector with everything perfectly aligned. So to be more realistic, what I'm going to do is define unit vectors that point along the arms of some given gravitational wave detector. Okay, so x hat and y hat are in a right-handed coordinate system with the normal to the Earth being the z direction. They define the two arms of the detector. And I'm going to define a detection tensor, which is basically just built out of outer products of these things, like so. In my last lecture, and this is stuff that Badri used in his lecture earlier this morning, I showed you how the gravitational wave tensor can be built out of the fundamental polarizations, the H plus and the H cross. And these polarization tensors, those polarization tensors, recall, are related to vectors that define a preferred orientation of the geometry of my source in the sky. I'm going to have an illustration of this in just a few moments. You don't have a saucer today that I can borrow. That's okay. I will make do. I'll use a different prop today. No, it's quite all right. I can use my phone will be my prop today. No, it's fine. I'm joking. So these are quantities I introduced last time. And so in general, the way I get the shift in the arm length is by doing a double contraction of my wave field with this detection tensor. Okay? And in very similar language, maybe a few of the symbols were slightly different. This is what Badri Krishnan reviewed for you this morning. When we put these together, so the combination of these polarization tensors with this detection tensor ends up defining what are called the antenna response functions, which I believe also appeared in Badri's talk this morning. I confess I had a high priority email and I missed some of that slide, but I believe you had that here. Yes, that's right. So if you imagine that here's my gravitational wave detector, and I define, let's say this is the x-axis, this is the y-axis, z-axis points along my head. If I define spherical polar coordinates according to those axes in the normal way, then theta and phi denote the position of my source along, in that particular coordinate system. The angle psi, which I'll describe in a bit more detail, Badri also went over this, but this is someone that's a little bit confusing. I find it useful to describe it again. This is the so-called polarization angle. So two of these angles tell me where the event is located in spherical coordinates. The angle psi, so again, imagine that I have my source, I'm looking at it on the sky. And let's say it's projected in such a way that I see an ellipse of this thing projected onto the sky. I will define the unit vector p to point along the major axis of that ellipse. If p is parallel to my x-axis, then the angle psi is equal to 0. Otherwise, it essentially defines a rotation between that particular preferred frame and what my detector has actually achieved. That's sort of nice. It turns out there's actually if you want to actually calculate it, there's a lovely expression that was derived by Kurt Cutler in a paper that it was designed for LISA purposes, but I think that the result carries a little bit more generally. So if n hat defines from the vertex of my detector, it points from the vertex of my detector to the event on the sky. L hat is the normal to the plane associated with my detector. This ends up defining this angle psi. Okay, so at the end of the day, the important thing for us is that we have this quantity that depends on It's a total of, so there's 3 angles that sort of specify it's the geometry of the way that the detector responds, and there's a 4th angle that defines the ratio of these 2 polarizations. At the end of the day, there are 4 angles that describe this thing. And you can think of them as the 4 angles that define these 2 unit vectors that define the geometry of the source. There's a unit vector which I would call n that defines the sky position. So when I use this language here, n is the thing that points to where it's located on the sky. And then there's another set of angles that define the geometry of that source, where it's normal to its orbital plane, if it's a binary, where that is pointing at that location. So it's important to get a lot of this geometry correct, because a lot of this stuff we're going to, you've seen this already in some of Badri's talk, and I will go into this a little bit more detail in my next lecture in particular. These all encode, this is one of those things where, many of us go into this field because we're sort of drawn to the beauty of solving the Einstein field equations, and we want to know about the wiggling of metrics and all the strong field stuff. But at the end of the day, there's just a fair amount of just kind of like crap that you need to cut through to get to that fun stuff. And these are very important details that if you do not understand how to convert from where it's located in the sky and how it's oriented, you're not getting all that interesting stuff about strong field gravity and binary astrophysics. So the sensitivity. So this I've described to you now essentially the geometry of this effect. You can sort of see how it is that a gravitational wave comes in, how it causes the length of the detector to change, how that length scale, how sort of these extrinsic effects having to do with where the source is on the sky and how it's oriented affect this thing. But at the end of the day, you also still have to measure a length change that's this. So the way we do this, and again, Nurgas Mavavala will go into this in a lot more detail, but I can give you the basics of this, is we are looking for the impact that it has on the phase of light. So it's important to note that what I'm about to say really only holds that the gravitational wavelength is much larger than the length. Okay, and I will show you, actually, Badri included in his talk a formula that does not have that restriction put into it. For developing the intuition, though, I will keep this condition imposed. So the phase shift on the light as it travels down this beam tube, it's directly proportional to the proper distance that the light travels as it goes down here. And a heuristic formula for this is that the change in phase due to the gravitational wave, you get a factor of 2 because it goes down the arm and back. B is a heuristic way to refer to the number of times it actually bounces back and forth in your beam tube. A professional would actually write this in terms of the finesse of a Fabry-Perot cavity. I am delighted not to be a professional because I can defer to the professional sitting off on the side here. I'll just refer to that as heuristically the number of times it bounces, which is on the order of several thousand. Here's the length change that's imposed by the gravitational wave, and this is the wave number of your laser that's going into this. As I've emphasized a couple times, when lambda is not much greater than when the wavelength is not much larger than the arm length of the detector, you have to be a little bit more careful. The paper that I should have cited that one as well. You cited this nice paper by Wahlquist and Estabrook. There's a really nice write-up that's similar to theirs. It was derived by Steve Detweiler, who very sadly passed away about 2 years ago of a sudden heart attack. He derived this in the context of making measurements with pulsar timing. And then a somewhat more pedagogical presentation of this was put together by Neil Cornish, which you can find in the archive. And these both do a really nice job of laying this out. All right, so let's move on. Those of you who were at my lecture last night saw a piece of this already. So if we sort of imagine a gravitational wave that is perfectly lined up, then what we would find is that the phase shifts associated with the change in length of my 2 end mirrors here are exactly opposite from one another. Okay, so whereas I would get destructive interference in the absence of a signal, when a gravitational wave comes along, it messes up that wonderful interference pattern, and in principle, I should then be able to use that to detect a gravitational wave, or at the very least to put together a control system which holds the interferometer on a dark fringe or close to a dark fringe so that I can read out the presence of a gravitational wave. Now, the fact that my two arms here come in with exactly opposite sign makes it look like this is serendipity. I'm looking for quadrupolar gravitational waves. This gives me a factor of 2. I can take advantage of that. That seems like a really wonderful thing. It seems to be the perfect shape to get out a quadrupole signal. And it is, especially if it happens to be exactly perfectly aligned, which never happens. In truth, the L-shaped arms have a different reason that's a lot more practical. And it was Nick Smith, one of Nergis's graduate students, who taught this to me after I made an incorrect statement about this at a different summer school about 12 years ago. So we basically would only expect there to be partial enhancement. That factor of 2 would be a factor between 1 and 2 for your average source. The more fundamental reason why the L shape is used for a detector like LIGO is that it helps us to suppress a very important source of noise. So when I go through, hang on a second. When I go through and feed into my, my detector all of this stuff, I'm assuming in all these theoreticians' calculations that my laser is perfect. It has a wavelength lambda. I put it in there and it's an absolutely perfect sine wave with a wave number 2 pi over lambda. That never happens, okay? There's always a little bit of noise associated with, the laser that's sent into this. So when I send my laser light into the interferometer here, the phase of the laser itself will be contaminated by a little bit of noise. But as long as you have a high quality beam splitter here into which your signal is sent in, the same laser noise goes into the X arm as goes into the Y arm. And what this means is that although the gravitational wave, the phase imposed by the gravitational waves have the same sign associated with them, I design a readout system that is sensitive to the difference in phase of the X arm versus the Y arm. And because my X arm noise is exactly the same as my Y arm noise, the variable that I actually read out cancels it. And if you do this perfectly, your interferometer is not sensitive to the laser phase noise. It cancels out. There have been a couple of proposals for sort of creative gravitation wave detector designs over the years that are based on essentially one arms. And several of the people who've done this have over the years, I don't think they've quite got this lesson that you get a factor of, the reduction is like it's a factor of 10 to the 10 or something like that in the noise, isn't it, Nergis? It's 1,000, okay. Pardon 1,000. But that's what, if you didn't have this, then the actual gravitational wave would be lost in noise by a factor of 1,000, essentially. I'll never forget one of them presenting this and Ray Weiss saying, what about the laser noise that you're using in your readout system? This is something that, if you do not suppress that here, and that's why we have the L-arm design, I have a hard time understanding how you will see a gravitational wave in the presence of your laser noise. And this person said, well, you just need to make your lasers better, right? Why don't you just make your lasers better? And he said, we've been trying to make the lasers better for 40 years. At any rate, let's just say that smart people have been working this for a while. This is why you make an L-shaped detector. All right. Now that's why you make an L-shaped detector. You get that antenna pattern, which is good, but not the fundamental reason. You kill this very important source of noise, which is the other one. Now, there are other things that we need to understand. So a fundamental one is how well, even let's say you cancel that out perfectly, how well could you measure the phase shift that is imposed by the gravitational wave? Now, we've already shown that for an optimal arrangement, this is the phase shift that you would end up getting coming out of your gravitational wave detector in the variable that you tend to read out. Now, when you actually read the laser, bear in mind, especially at the frequencies we're operating at, there is going to be a little bit of what's called shot noise imposed on that signal. That's just reflecting the fact that light is quantized. And so there's no reason this is a wiggly equal here. Roughly speaking, the amount of shot noise associated with your measurement, it imposes an error in how well you can read the phase of your output laser light that, as this formula shows, scales as 1 over the square root of the number of photons gathered in your measurement. Okay? So if over the course of your measurement you average over, let's say, 10 to the 12 photons, then you'll have a shot noise that scales as 10 to the minus 6. At a higher frequency, you're averaging over shorter times, and so instead of averaging over 10 to the 12 photons, you might only average over 10 to the 10 photons. So your shot noise now scales as 10 to the minus 5. It's still low, but it's a factor of 10 larger than it was at your other frequency. So in general, the number of photons that you measure in the course of a measurement, heuristically, you can think of it as your laser power, a factor that essentially is the energy of a single photon, the time over which you actually make your measurement, which is something like the averaging time associated with the measurement, 1 over the frequency you were doing your measurement at. And then a practical factor, really this eta goes with this eta is a quantum efficiency of the light measurement. It shows you how well you can measure out this power. P times this eta is kind of like an effective power that goes into this little calculation. So when you put all this together, what you find is that roughly speaking, the gravitational wave signal will win if the quantum efficiency times the power of the laser is greater than about 100 watts. That's just to achieve parity across the band that we're interested in. You really need a lot more than that if you want to beat it down and get really good signal-noise ratio. And this tells you that you need a good product of these two quantities. You need a lot of power circulating in your arms, and you need good detectors, good quantum readout devices. I will leave the details of how you do this to my laser colleague who knows. I've essentially at this point exhausted my knowledge of laser physics, so I will stop embarrassing myself and move on. So that's great. There's a lot of other noises that we care about too, and to sort of put them in context as to what we care about, it's worth sort of imagining that the gravitational wave, it comes along here, and as I've emphasized in yesterday's lecture, it acts in sort of a tidal way. And we can just picture what the sort of the effective force is that causes two masses in the detector to move apart from one another by using this equation here. So I can estimate the magnitude of the tidal force that causes the test masses in a detector like LIGO or LISA to move apart from one another by scaling it to the curvature that arises from a gravitational wave, the separation of the test masses, and the mass of those test masses. When I plug in the parameters associated with, so I use the fact that the curvature tensor is roughly frequency squared times the wave strength, and then I plug in the parameters that are in a detector like LIGO, what you find is that the gravitational wave is effectively exerting a force for the kind of sources that are being measured right now that's several, up to about, between 1 and 10 piconewtons. So what should you take from this? Okay, this is actually, I found this when I have given talks at my university and a few others, and I'm talking to non-physicists, particularly when I talk to biologists. This suddenly makes them go, oh, that makes LIGO make a lot more sense. Because this is basically the weight of an animal cell. And people actually measure the masses of things like that all the time. They don't do it quite, this is a bizarre scale for doing that on, but it sort of demonstrates that the kind of, what this is saying is that since my gravitational waves are exerting a force that's several piconewtons, I need to make sure that all sources of noise in my instrument exert less than that amount of force if I want my gravitational wave to stand out. And what this calculation makes clear to people is that this is hard. Okay, you should not imagine I'm saying it's easy. This is an extremely difficult endeavor, but it's certainly not impossible. So at the end of the day, a lot of what goes into making a detector like LIGO and Virgo work is controlling all the forces, all the noise forces, such that they are smaller than this effective force that is generated by a gravitational wave. Now, I'm going to describe a little bit of the mathematics that underlies the spectral density that played a starring role in some of Badri's lectures today. Noise arises from a random process. Okay? If it's not random, it's not noise. So we need to develop some mathematical tools for characterizing these. And so the discussion I'm using here is actually adapted from a textbook that was recently written by Roger Blanford and Kip Thorne. Many of us sort of suffered through a course when we were graduate students at Caltech as this book was being developed. I started my PhD in 1993, and the book was going to be submitted for publication the next year. The class that started in 1994 was told to be submitted for publication the next year. The class that started in 95 was told blah, 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 blah. The book was actually published in 2015 or 16, so it took a little while to work the bugs out. All right, so let's suppose I have some function n of t, which describes noise at some moment. We're going to be interested in characterizing its statistical properties. So suppose the average value is equal to 0. If it were not, then that basically tells you you've set your 0 wrong. So it should be 0 if it's truly noise. The most important properties of this are going to be captured by the correlation function, which basically tells me what is the relationship between n at time t versus n a time tau later. This sort of tells me how it is that the noise evolves as I wait. If I know what it looks like right now, what does it look like if I wait 1 second, 1 millisecond, 10 seconds, okay? And so this correlation function tells me a lot about what the properties of the noise are and how it evolves as a function of time. If I look at this thing's value when I compare it to an offset of 0, that's just the variance associated with the noise. Now, for a lot of the analyses that we do, it's actually more useful to characterize these things in the frequency domain. So let's define the Fourier transform of the noise like so. In truth, when you take the Fourier transform of something, it tends to diverge. Okay, if you have a function that just is always oscillating, it's got power on lots and lots of scales, and you integrate it over an infinite amount of time, you get something that just isn't very well behaved. And so what we do is we introduce a quantity which normalizes this divergence. This is what that spectral density that Badri used in his lecture, where it fundamentally comes from. So as I take the limit of t going to infinity, this is exactly this Fourier transform here. But I'm going to normalize it by the interval over which I'm doing the calculation, and I'm taking the modulus squared of this thing. And as Badri showed you, this is a quantity which has units if my n is dimensionless, because I'm measuring gravitational waves which produce a strain. It's a length over a length. It's dimensionless. This has the units, so this will turn into time squared divided by time. People actually know as inverse hertz. Okay? I'll describe why that is in just a moment. Here's why. So by connecting all the various definitions that I've put up on these different screens, it's not hard to show that the total variance associated with the noise in my detector, so the offset 0 correlation of the noise with itself, is just given by integrating the spectral density over all frequencies. By the way, this factor of 2 here is related to the fact that I'm only going to define this thing for positive frequencies. Suppose you are only doing a measurement, going down to 0 and up to infinity is not useful for most experimental purposes. So if I only care about the frequency in some particular band, I get the variance of noise associated with that band by just integrating over that band. And this, incidentally, is why we tend to talk about this thing of having units of inverse hertz. It's because I'm going to integrate it over a band of frequency and get a dimensionless number out of it. But what actually is the noise? So what can I do with that spectral density? So let me walk you through a little bit of an example. Suppose I have a damped harmonic oscillator that is in some kind of a thermal bath. So the spring might be warm. It may be in an atmosphere that's interacting with it. But I'm not going to actually force it. I'm just going to let it sit here. Okay? And so the motion of this thing is going to be governed by the following differential equation, where gamma is a damping associated with the mass spring system. And the delta F here is essentially a noise force. So this is the force that's due to all the various elements of the thermal bath that are buffering this mass spring system. There is a remarkable theorem that allows us, it essentially connects the properties of the damping to the properties of the random force that is buffering this. So this is, I'm not going to prove this theorem. You can find it proven in some higher level statistical mechanics books. But it tells you that the spectral density associated with that force is determined by the damping coefficient and the bath temperature. So with this spectral system here, so again, I don't necessarily know exactly what this delta F is, but I know that its spectrum is flat with respect to frequency, and its magnitude is given by this. And that allows me to determine the statistical properties of the force that is acting on my mass. And then once I have this, I can easily go back to the equation of motion here, analyze this in the frequency domain, and work out what the spectral density associated with the displacement of the mass on the end of the spring is here. And so what I would see in this case is that just from sitting here, this mass will tend to wiggle around due to the various thermal bufferings that are thermal impact of things that are hitting it, with a spectrum of displacement given by this. Integrate that over all frequencies. You can use that to find what the mean, what the variance is associated with this thing's wiggling over time. Now, quantities like this are what we fundamentally use to describe the noise spectrum of a LIGO detector. You can kind of think of every one of the little terms that's going into here as describing, in many cases, a mass spring system kind of like this. So let's look at the way this behaves for different gravitational wave antennae. So what I'm plotting on the vertical axis here is the square root of the spectral density. That, up to a factor of integrating over a frequency band and taking a square root, that describes essentially the gravitational wave strain that you are sensitive to, and then looking at this as a function of frequency. So the curves I'm actually showing you here, these are taken from some LIGO document that I downloaded over a year ago. They're probably already out of date at this point. But roughly speaking, this blue curve shows us what the sensitivity looks like in the O1 run. The green curve, I really wish I remembered where I took this from, but it's approximately the sensitivity that is being aimed at for next year. Again, I'm not quite sure. And red is the final design sensitivity that the detectors are aiming at. Let's talk about the different pieces of physics that govern this. So at high frequency, this is the place where the detector sensitivity is limited by photon shot noise. Okay? As I go to very, very high frequencies, the number of photons that I gather in an interval 1 over frequency is getting smaller and smaller and smaller. And so I am less able to accurately determine the phase. I don't measure the gravitational waves as well. Here in sort of mid-base, currently, it's being limited by thermal motions of the pendulum. So that heat bath that I described to you of a mass spring system sitting in a thermal bath, that is essentially what is going on right here. As the detectors improve, we expect that it will actually be limited at these low frequencies, roughly the same band, by radiation pressure. So when you turn on a very strong, in order to get good sensitivity over here, you're always going to be limited by the fact that as you go to higher frequencies, you are getting worse shot noise because you're integrating over less times. So you can compensate for that by making the power in your laser larger. But lasers don't just put out energy, they also put out momentum. And that momentum has fluctuations associated with it. And so down here, as I make the laser power higher, eventually I start having little random kicks due to the pressure exerted by the light itself. And that is expected to be, in the most advanced, in the design sensitivity, what ultimately limits the sensitivity in this band here. In other words, about how far off are we from being dominated by radiation pressure versus thermal noise in this band? Is this something?
I will show you tomorrow.
This is something where one of the world's experts on making this work will be your lecturer tomorrow. The lowest frequencies of all, you're eventually limited by the fact that, as I've emphasized several times, we're doing these measurements on Earth. Earth is a noisy place. If you build a really good suspension stack, you can isolate it such that you're completely insensitive to gravitational waves sort of below this, but you're totally sensitive above this. And you have to choose which frequency to do that at. And that depends on things like how long of a pendulum you can make. Okay? The response of a pendulum is square root of g over L. That's the natural frequency of a pendulum. So if you want to go to lower frequencies, you need a lot more L. You need a really long pendulum. That starts to get hard because we have finite space to build these in. It's also the case, even if you had a perfect pendulum, you would actually couple gravitationally to ground vibrations. And since you want your detector to be sensitive to gravity, you really can't get away from that. So let's talk a little bit about the way some of these concepts apply to LISA, the space-based detector. So this is being designed as 3 free-flying spacecraft separated by 2.5 million kilometers. So they sort of fly in an orbit around the sun like so. This has been selected for, in the language of the European Space Agency, the L3 slot. L stands for large mission. And so I believe L1 was a mission to study the moons of Jupiter. L2 is an X-ray telescope. L3 is us. So currently slated for 2034. Stay tuned for that. So the basic idea of this is that we have these 3 spacecraft independently orbit the sun. And they are moving, they sort of have a triangular constellation. The centroid of that triangle lags behind the Earth by somewhere in the vicinity of 10 degrees to 20 degrees, depending on the mission design. And as they do so, the triangular pattern kind of rolls, as is illustrated here. So eventually, this orbital pattern will fall apart. The reason being that, kind of like I emphasized in my public lecture yesterday, we don't just have a system. It's not just things orbiting the sun. They're affected by the Earth, they're affected by the Moon, they're affected by Mars, they're affected by Jupiter. And the tides of all these other objects actually eventually make this constellation fall apart. The mission is planned to be funded for a 5-year nominal time frame, but the orbits have been chosen so that it should last for about 20 years. So I've already gone through a lot of the measurement concepts and applied them in the context of LIGO. Fundamentally, things are similar for LISA, but there's some important differences. One is that the arms are a lot longer. Okay, so it's still the case that the h you are measuring is something like delta L over L. So for your ground-based detectors, the kind of systems that we are looking at tend to be stellar mass bodies, black holes and neutron stars from about 1 or 2 solar masses up to 30 or 40 or 50 solar masses. And what we find is that in our frequency band, the typical strains are part in 10 to the 21. So for a separation of kilometers, that leads to a fraction of a thousandth of a femtometer being your typical kind of scale that you're trying to measure. In space, our sources are a little bit louder because they tend to be more massive. Okay, they're also in a different frequency band. So the kind of things we're measuring are, we gain an order of magnitude because they're somewhat higher strains. We also gain quite a bit because it's not 1 kilometer or several kilometers, it's several million kilometers. And so the length shift that is being measured is actually several picometers. Okay, that may seem, again, that may seem small, but it turns out that is within an order of magnitude of the fringe shift that was actually measured by the original Michelson interferometer, which did the famous experiment of showing that the speed of light did not depend on season. Okay? So this was done by Albert Michelson in, I should know this year, around 1900. And it was done using a sophisticated measurement device called the eyeball. Okay? Using some of the techniques that are available now, we can do a little better than that. It's also the case that he was measuring this, he was not looking for a modulation at a particular frequency, which makes it a little easier to pick out an effect. He was integrating in real time with his eyeball. It was basically a DC effect, where noises tend to be a little more difficult to control. I borrowed this whole thing from Karsten Dansman, who was very enthusiastic about this analogy, because it really shows that, at least as far as the laser metrology goes, in LISA, it's relatively easy. What's difficult and is far more challenging is once you launch a spacecraft, it's gone. This is in an orbit that cannot be serviced. It's trailing the Earth by 10 or 20 million kilometers. You throw it up there, and then you discovered that you forgot to pull a bolt off of it. Okay, well, there went €500 million. Sorry, dude. So there's a tremendous amount of work that is done in advance to demonstrate that the noise budget can actually be met in a free-flying spacecraft. And so this was actually tested by a mission that was flown by the European Space Agency called LISA Pathfinder. It launched. It was very interesting being in certain circles at this time, because everyone was really busy trying to sort of, for much of the time while we were getting ready for launch, this was after the first LIGO event had been measured, but before it had been announced. And then in the meantime, they're getting ready to get this thing that many of my friends had been working on for ages and ages and ages, that launched while people were in the thick of doing these analyses of the first event. It reached the L1 Lagrange point, which sort of trails Earth. It's in the Earth-Sun system. Which one's that? That's L4. So it's over here between the Earth and the Sun. And began science operations a few weeks after the press conference in which the first LIGO discovery was announced. So a lot of people were very nervous about this, because the performance of this was going to really demonstrate whether LISA could be made to work or not. So here was the result. So this is a spectral density of acceleration noise as a function of frequency. LISA Pathfinder was required to be at, or if possible, slightly below this curve. with the thinking that if you could do that in the pathfinder, it would be possible to extrapolate, basically because it's in a different orbit, it's in a somewhat quieter orbit, that you would be able to measure things with LISA on this curve. After it had been in operation for a little bit more than a month, it was announced that Pathfinder had actually achieved a noise curve that looked like this blue streak here. It beat its spec by more than an order of magnitude over a much wider band than had been expected. As further time passed, essentially the spacecraft settled down a little bit. An entertaining piece of this is that you design these things in a vacuum system, but there's always going to be a little bit of residual gas that gets absorbed onto the metal. In some cases, it actually gets dissolved into the metal itself. And so a big part of what happened while it was in orbit was just last little bits of gas would occasionally sort of come out of the spacecraft and improve its performance. And so after an additional almost year of operation, the noise pushed down by another factor of about 4. And with additional time on band, they were able to show that they could go significantly beyond the original bandwidth that was met. It became very clear that Pathfinder was far more successful than we expected it to be, which was good because it was significantly more expensive than it was expected to be. It turned out to be a very hard thing to make. There's a rule of thumb that a space mission costs roughly a factor of pi more than you originally expected to. And that is almost exactly what happened with this. But the money was very much well spent because it really demonstrated that they could achieve the LISA requirements. And LISA clearly became within reach. And so that's one of the reasons why the mission is now very actively being pursued. So let's look then at what the projected budget is likely to be, the noise budget is likely to be. So here, this red curve here is the equivalent of the noise curve for LIGO we've been showing you. That's a spectral density of noise that is expected for LISA measurements. Now at high frequency in a band that looks right about like this, actually let's do low frequency first. So at low frequency, we're taking advantage of the fact that the acceleration noise is approximately constant as a function of frequency. If the acceleration is constant as a function of frequency, then the displacement will go as f to the minus 2. So that's all we're seeing here is essentially a flat spectrum of acceleration noise translated into a displacement, which translates into a gravitational wave signal. At high frequency, you start out with that same sort of shot noise slope that we saw with LIGO. This is just measuring fewer photons as you go to higher and higher frequency. But you'll notice there's some oscillations that happen here. The oscillations come about because in this regime, we are no longer in this region of the spectrum. We are no longer in this regime where the arm length is larger than the detectors. Okay? So up here, the wavelengths that you are measuring are actually smaller than your detectors. And in particular, at every one of these little peaks, those correspond to a gravitational wave frequency that is actually an integer multiple of 1 over the light travel time down the gravitational wave detector's arms. And it can be shown without too much effort that at least for certain directions, the detector arms for which you are try that sentence again. When you are on this condition where the frequency exactly sort of is an integer match to 1 over the light travel time, you completely become insensitive to gravitational waves, at least from certain directions. And the reason for this, imagine I have my gravitational wave detector like this, and the gravitational wave comes down my arm. What I end up happening is if the light travel time is exactly equal to the period it takes for the gravitational wave to stretch and squeeze this arm, I get half the effect on the one side, and then it cancels out on the other side. Okay? So when you are on this case, for the directions where it lines up perfectly with the detector, you lose sensitivity. Now when you average overall sky directions, you wash that effect out a little bit, but you're left with these residual oscillations. Another issue, which is fairly interesting, and it's something that is quite different from the experience with the ground-based detectors, is that when one is analyzing the data from the ground-based detectors, generally what you are listening to, if you were to put your earphones on and listen to what LIGO is hearing right now, it's noise. Okay, you're always just hearing sort of the white noise that generally, whitish noise with some frequency shadings associated with completely random noise, and occasionally something going whoop. Okay, and those moments of whoop are, they're celebrated. People win Nobel Prizes for them, at least one. So those are a big deal. The sources for LISA are expected to last for months to years and happen dozens to hundreds of times per year. That tells you that there will actually be multiple sources on at the exact same time. So there's a very different data analysis challenge that people are just now really, I think, facing up to. Well, just now is a little bit of overstatement. That for the past several years, people are really facing up with how to deal with, which is that you're going to have multiple very loud sources that are all speaking at the same time. So instead of trying to get the one quiet voice in this noisy background, instead, you're going to have dozens of things on at the same time. Okay, that's annoying. There are several, I was hoping I think I might have had the volume a little too low to catch it. There are several big black holes chirping in that thing. What's kind of entertaining is this is, of course, vastly sped up so that the human ear could hear it. Many of the people who designed the optical readout system are based at a university in Glasgow, and that sounds strikingly like bagpipes to many of us, which perhaps tells us that we just think bagpipes sound terrible. All right, so a major application of what you want to use, and this sort of feeds into, again, some of the stuff that Badri talked about in his lecture. What do we use the noise spectrum for? It's to design the optimal filters that we use to make our measurements. So in many cases, your gravitational wave is actually, the instantaneous amplitude of your source is significantly smaller than the mean amplitude of the noise. That's actually something about that initial discovery event. That was, for many of us, one of the most surprising things about it, was that it was so loud. Once there was actually sort of the signal was band filtered, so that it was only looking at power in the band from about 30 or 40 hertz up to about 250 hertz. It stood out above the noise without any additional detailed analysis. That's not typical. And so what you need to do is correlate the data with some kind of a filter that can pull the signal out of the noise. So let me denote k of t as being some kind of a filter function. And what I want to do now is say, what would be the best filter I could use if I'm looking for a source that I believe I understand? So I'm going to define a detection statistic, y of tau, to be what I get when I do a cross correlation of my data, which I will call S for signal, with this filter. Okay, so I'm going to define that as my statistic. I'm going to define the signal-to-noise ratio. So the signal is essentially given by taking the average of this thing. And when I take the average of this, remember, I'm assuming that my noise has 0 average. So the noise goes away. And if I take this thing and then write it, this S, which I can think of as, let's say there's a gravitational wave present. It's the gravitational wave signal H plus a noise. Its average, the noise will go away. So when I transform to the frequency domain, this cross-correlation integral turns into this. For my noise, I want to look at the average of this, the root mean square average of this, under the assumption that there is no signal present and it's nothing but noise. If you trace through all the various definitions that I went through earlier in the talk, what you find then is that your noise turns into this integral here. So this is all, I don't want to go into the details of this. Anyone with a little bit of stamina goes back and traces through the earlier definitions can verify these formulas. So what we would like to do then is find the filter that gives me the highest possible signal to noise for a particular signal. And it's not a lot of effort taking this formula here to prove that the optimal filter for this thing is given by, in the frequency domain, your optimal filter is given by, you take the Fourier transform of the signal that you are looking for, divide by the noise spectrum. And when you put that all together, that tells you that the signal to noise ratio you read out of this thing is given by a formula that Badri wrote down probably at least 4 times in his lecture this morning. And the particular use for this, and I will go into this a little bit in my final lecture, and this tied into a lot of the stuff that Badri talked about this morning. If we assume that we have the correct theoretical description of our waveforms, this optimal filter, what we essentially do is we just populate exact theoretical models for the waveforms parameterized by whatever knobs and buttons are attached to our model. So my theta sub I here, those might be the different masses, they might be spins, they might be things related to the finite size of a neutron star and how that can affect the gravitational waveform, or the equations of state. If I am interested in exploring physics beyond Einstein's general relativity, some of my theta sub I might be corrections to this thing. Then all I need to do is build a template bank that covers the space of what my detector is sensitive to, essentially compute statistics like this over and over and over again. That's part of what underlies, sort of, we probably should have gone the opposite order. It then underlies all the calculations that Badri gave you today. I'm going to stop here so we can take a little break, and then what I want to talk about in my fourth lecture is the science that we get out of this. Most of you don't have the excuse of jet lag, so.
Assuming we have enough time and enough SNR, is there any test for GR or alternative theories that cannot be done with a single LIGO detector, but with a different topology or
Can you hold that question to the next lecture? Because that actually feeds directly into some of the things that I'm going to talk about. Yes. You know, I'm just thinking over that talk. Actually, I will begin to answer that a little bit. So one of them is, suppose there are polarization states beyond the H plus and the H cross that I described here. Suppose there existed a state of the gravitational wave that is not transverse to the direction of propagation. You would need multiple detectors to be able to feed that out, to pull that out of there. Because, you know, a single detector basically reads a particular superposition of the two polarizations. Okay? Two detectors, you can sort of begin to, depending on how they're oriented, pull out a few more polarization states. You can get more information about two polarization states. Basically, the more detectors you have, the more you either over-constrain the solution for two polarizations or make it possible to look for additional polarizations beyond the standard two of general relativity. That's probably the most, the one for which multiple detectors at least is probably the most important, I would guess.
How does the triangular shape of LISA compare with the L?
That's an excellent question. So, I didn't have time to talk in much detail about how the LISA measurement is actually done. It does not bounce light back and forth. Okay, so what is done is, you know, it actually takes light something like 10 or 12 seconds to travel from one spacecraft to another. And so on each spacecraft, there are two lasers pointing sort of downstream to the other two spacecraft. And then there's a telescope that is reading in the light that it receives from that spacecraft. Bear in mind, this is diffraction, right? So to first approximation, those lasers, you know, it's essentially laser pointers, right? So this is what's going on, is it's pointing this at the other spacecraft. Now, this makes a spot that's about, let's say, 2 or 3 millimeters across. And as it goes across the room, it's still about 2 or 3 millimeters across. But if I were to send this 2.5 million kilometers, there would be a diffraction effect start to set in. You're well into sort of the different zones associated with light propagation. And when that spot reaches the distant LISA spacecraft, it's actually about 40 or 50 kilometers across. Okay, so you're reading a relatively small fraction of that light that comes out of that thing there. Nonetheless, you get enough that you can actually accurately read the phase of this thing. And so then there's onboard electronics that allow you to sort of difference. You're using your own local laser as a clock to beat this against and ascertain what the fringe rate is of that distant laser versus yours. And you're essentially looking for you are then looking for oscillations in the difference of phase between your local clock and the clock associated with the laser that's been sent towards you. So because of that, you're not bouncing light back and forth, and so it's a little bit of a different optical topology. There's actually very complicated schemes for combining all these different difference phases to remove the laser phase noise associated with that. So as far as using the L to get that gain of laser phase noise, it just doesn't work for LISA, and there's a very different scheme that's used. Then the question becomes, what is the antenna response function associated with this? At least for very long wavelengths, it turns out, this is a little bit of a miracle, but it's one that proved very handy for certain papers that I wrote 15 years ago, that if you think of LISA as, it's a triangle like this, this can be regarded as a superposition of a detector, an L-shaped detector like this, plus another L-shaped detector rotated by 45 degrees. And so the triangle pattern, when you do this, let's say this side is of length L, so these sides are all L. These sides end up being square root 3 over 2 times L. Same thing for the other one. So slightly shorter arms, but this triangle is the equivalent of 2 L-shaped detectors, at least when you're in the regime in which the wavelength is greater. So this works for LISA for its low frequency sensitivity. It gets a little bit more complicated because of those wiggles and a few other things. But what this means in terms of, I'm going to talk a little bit in my next one. I believe Badri went over this a little bit as well. When you have 2 independent detectors, it becomes possible to measure both polarization states from a given gravitational wave source, right? So if I only had one L, so a given L, depending on a particular source, it reads a particular superposition of the 2 polarizations of the gravitational waves. But if I have 2 of them here, I basically have completely independent antenna response functions. And so I measure 2 different superpositions of these things. And from that, I can detangle what the independent polarizations are. Okay, so a big benefit of the triangle shape is that you get additional polarization information about your source, which vastly helps you to do a lot of the science you would like to do. I will make one little comment, which is that a number of years ago, so about 10, 12 years ago, there was a particular LISA mission that many of us worked on for quite a long while, which is basically based on this design. Then the American Space Agency kind of lost its mind and had to quit. And the European Space Agency decided to go on independently. They determined that they could not afford to do the 3-arm design. And so they made a design that was only 2 arms. And when you do that, well, you're only getting one of these things. It's not quite as good because it's not an L. It's sort of a wedge it's a wedge. And the astrophysical payoff was basically, to first approximation, it turns out it did not save that much money, but it did seriously impact the science. So fortunately, it was not that difficult to convince people to put that back in. The way that this worked here is that I actually have an old graphic from this intermediate era when they were working with 2-arm detectors, and it's prettier than some of the ones that are available now, so I just took my plotting package and I drew an extra arm in myself. All right, shall we take a short break? All right.